Welcome back to ECE 220. Start with a little class participation. What's happening in a week? You will have your first exam a week from today. Just getting you psyched or focused for that. That's the last announcement, but if you need practice on that, you should be able to find that on D2L. Homework 4 is due on Tuesday. And Saturday, you have nothing more to do than to do your pre-lab, which is due on Saturday for the 4 sections, E, F, G, and H. If you need help, the TAs are in office hours during the week, Monday through Thursday, 11 a.m. to noon, and I have my office hours actually Friday, 11 to noon, and today right after class. Your pre-lab, make sure you compile all of your material, whatever that ends up being, into one PDF file. And I believe yesterday you received an email from a TA saying how to label or name your file. But all of those files that you will submit will go into a particular Dropbox. There should be a Dropbox or an assignment folder for you to submit your particular pre-lab and lab into. These 4 sections, turn your lab in by Saturday. We're going to continue with mesh current analysis, MCA. Today we'll talk about, or we'll examine an example with dependent sources, and then we'll look at the dual concept that we had with supernodes. We now have supermeshes. And how do we work with current source components that are sprinkled around or in our particular electrical network? And there's there's two cases that you could encounter. One is if that current source element, dependent or independent, is in only one mesh, then that actually allows you to reduce the number of mesh currents that you might have originally labeled. If there's a current source component that is in more than one mesh, let's say it sees 2 different meshes, then we'll have to implement the supermesh idea to make our job a little bit more straightforward in terms of the analysis of a circuit involving that kind of a current source component. Let's start then with an example using mesh current analysis, MCA, when we have a dependent source in our circuit. Here's the circuit. If it's not labeled, then the resistors have units of ohms and the voltage supplies have units of volts. And our goal in this particular circuit is to find the power associated with the dependent source. And the dependent source is kind of mixed up, meaning we have polarity labels on the dependent source, and then that particular dependent source is specified to possess a voltage of minus 3 V sub phi, where V sub phi is identified somewhere else in the circuit, and that information would have to be supplied to you. You would have to be given the dependent variable, wherever or whatever that consists of, and how that then impacts your dependent sources. Here's the circuit, and we now want to know what's the power associated with that dependent source. And consistent with what we've been seeing in Chapter 4 is we can't immediately jump and write down the power. We have to iterate our way towards that, and here you can see, I hope, the mesh structure of this network. It's planar, and it's under the heading of mesh current analysis, so you can anticipate that we're going to be solving this with mesh analysis. Can you now identify the mesh currents? And those are distinct from the branch currents, and how you label this is really, it's not unique. We could have a lot of different ways of labeling this. I'm going to go ahead and say here is mesh 1 with mesh current I sub 1. The top one, let me go ahead and say that is now mesh 2 with mesh current I sub 2. And then the remaining mesh is in the lower right, and I'm going to label that as a mesh current I sub 3. That's really step 1, is identifying the mesh currents. I have I1, I2, and I sub 3 in that circuit. And it's not special how those are identified. I1 could have been the top one. But obviously our answers would be different in terms of how they are labeled, but we would get consistent results. However you label those mesh currents, we all should be getting the same power associated with that dependent source at the end. Meaning, if we now had, what is the power expression using the passive sign convention associated with that dependent source? What's the formula? The current is actually coming out of the positive terminal or going into the negative, so it's going to be this negative sign, isn't it? The voltage dropped across that dependent source. I'm going to call it V sub diamond, and then that's times I sub 2. We're going to need I sub 2, and we're going to need that voltage drop across that. So this is now what I'm saying is V diamond. And we'll have to then sort out. So V diamond is that voltage drop, which is minus V sub 3 V sub phi. Bottom line, we need to find the mesh currents. And they're coupled, so we're kind of probably have to find all three, and then we'll just claim I sub 2 at the end. Writing KVL then for mesh 1 is going to be minus 25 plus 2 times what expression? We're going from left to right, so that's saying I1 minus I2. Then we come down through the 5 ohm resistor, and that will be plus 5 times I1 minus I3 plus 10. That's KVL for mesh 1. Whatever I just said, that's now minus 25 plus 2 times I1 minus I2 plus 5 I1 minus I sub 3, according to how we've labeled the mesh currents, plus 10 is equal to 0. And there's one of our equations that we need. We're going to need 3. We have 3 unknown mesh currents. Now we can write KVL for mesh number 2. And here's where you need to just sort of keep track of the signs, SIGN. If I start in the upper right-hand or upper left-hand corner, I'm going to now go minus whatever that voltage is on that dependent source. And that voltage is actually minus 3 V sub phi. I'm going to write that then as minus 3 v sub phi. Just to be consistent. I was going in the negative terminal, and then it's whatever that dependent source is labeled, and it's labeled to have a value of voltage of minus 3 v sub phi. Then we have 14 I sub 2 plus 3 times I sub 2 minus I sub 3 plus 2 I sub 2 minus I sub 1. And then we're back where we started. The hard part was just writing down that first expression for getting through, or the voltage associated with that dependent source. And before we start worrying about v sub phi, let's just write down the third KVL equation. But we're going to have to get rid of that v sub phi. And here it's probably cleaner to not include v sub phi in our KVL equation, since we can express it, or we can avoid writing it, since it's actually 3 times I sub 3 minus I sub 2. If we start in the lower left-hand corner of mesh 3, it's minus 10 plus 5 times what's the current, and now we want the voltage dropped from bottom to top. Ohm's law says we need to know what's the net current going up through that 5 ohm resistor. The current going up net is I3 minus I1. Then we have the voltage dropped across the 3 ohm resistor from left to right. That's 3 times I3 minus I2 plus 1 times I sub 3. This is now minus 10 plus 5 times I sub 3 minus I sub 1 plus 3 times I sub 3 minus I sub 2 plus 1 times I sub 3. Any questions on where those come from? We're simply writing KVL equations. We now need to get rid of this v sub phi in the solution process. So this is now really, because we have a dependent variable, that now leads to a constraint equation, where the constraint equation in this case is really what is v sub phi. Now we go back in terms of the unknown variables that we're trying to evaluate or solve for. And that's I1, I2, and I3. We now need to find an expression for that voltage, that dependent voltage, v sub phi, in terms of I1, I2, and I3. We can find that by just applying Ohm's law. V sub phi is now 3 times I3 minus I sub 2. In the direction positive to negative, left to right. That will give us, or that 3 times I3 minus I sub 2 will give us the correct v sub phi. That's the constraint equation that we need here. And this equation can now be used there. We have two minus signs. A minus makes a plus. We have a 3 times another 3, so we actually have 9 times I sub 3 minus I sub 2 plus 14 I sub 2 and that's now equation 2 that we will want to use. That contains only the unknown mesh currents, I1, I2, and I3, and make sure I keep my subscripts correctly identified and the coefficients. If we simply expand or push all of these constants through, we can write the first equation in terms of I1, I2, and I3 equaling something. It's going to equal what's going to be on the right-hand side when we solve for that. 15, 25 minus 10. And we have 7 I1s. We have minus 2 I2s and minus 5 I3s. If we do that for all of these, then 1 gives rise to the following. That was 7I1 minus 2I2 plus, minus 5I sub 3 equaling 15. That's where that's coming from. Equation 2, which we've now improved upon because we've removed the dependent variable in that expression, if you combine all of those, you'll find minus 2I sub 1 plus 10I sub 2 plus 6I sub 3 is equal to 0. And finally, equation 3 will produce minus 5I1 minus 3I sub 2 plus 9I sub 3 is equal to 10. We now have a resistor matrix we could factor out times I1, I2, I3, this column or matrix of currents that are unknown, equal the right-hand side, which is our combinations of voltages in the appropriate way, 15, 0, 10. We can solve that for the unknown mesh currents. Yielding 4, minus 1, 3, and those have units of amps. Your calculator will just do the linear algebra, invert that matrix, or however it does it, to find I1, I2, I3, or you could solve that with 3 simultaneous equations. You could do that manually. You could do row reduction, find a reduced row echelon form, and back out the I1, I2, and I3. What were we after? Our goal was to find the power associated with that dependent source. If we plug this into a calculator, what would we have? What are the dimensions of the calculator? The dimensions of the calculator are about 3 inches by maybe 7 or 8 inches. But we need matrices, don't we? So we're talking about units of matrices. This would now be something. This is the R matrix times our unknown currents equaling the right-hand side, which we've now found is 15, 0, 10. Meaning, now, to be compatible, what do we know the dimensions of R, that R matrix, needs to be if it's multiplying a 3 by 1 matrix or a 3 by 1 vector and producing a 3 by 1 matrix or 3 by 1 vector? What are the dimensions of R? this is 3 by 1 to produce a 3 by 1, and this is going to be a 3 by 3 matrix. And the entries in that will be 7, minus 2, minus 5, minus 2, 10, 6, and minus 5, minus 3, 9. That's Ohm's law in matrix form.
So for multiplying two matrices in the calculator, plug the 3 by 3 and plugging in the 3 by 1?
It depends on your calculator what you're going to do with the calculator, but probably you're going to, I would say you're probably going to plug in the R matrix and then invert it and multiply by V to obtain I. Depending on how you want to solve this, you could plug in a matrix R, raise that to a minus 1 power, that's inverting it, and multiply it on the right by the right-hand side, which is V. That will yield this answer, 4 minus 1, 3. We now want to find the power of that dependent source, and here's our formula. P diamond is minus V sub diamond I sub 2. So the power of that dependent source is now minus, and it was, well, let me just go ahead and write it down the way the notation that I had used, but that V diamond was actually minus 3 V sub phi. And V sub phi was in fact 3 I sub 3 minus I sub 2. Or if we negate the minus, we then end up with 3 times 3, or 9, times I3 minus I2 times I2. And this will be, based on the passive sign convention, the power absorbed by that dependent source. Putting in our numbers that we've, let's just take a time out and I'll try to draw a diamond. Okay? I'll put it on pause. Oh man. That's in the cloud somewhere, but you know what it is. That's now our power. Somebody's signature. This is now going to be 9. What was I sub 3? That was 3. Minus I sub 2, which was minus 1. Times I sub 2, which is minus 1. We have to stick with the signs, S-I-G-N, that we end up with. We now have 9 times 4 times a minus 1. We have minus 36 watts absorbed. Or we could say the power, forget that, power is now 36 watts supplied or delivered to the rest of the source or to the rest of the circuit. See how that diamond has really messed me up? Questions on that? You just have to be careful with your signs. Let's now look at what happens when we try to apply mesh current analysis in circuits, and we actually finished with this at the very end of yesterday's class. We were talking about something like this. If you now see this circuit and you say, oh, I want to do mesh current analysis, how would you approach it? What's the first phase or step in that solution process? And here I haven't specified anything. We'll just solve it in terms of these R's and I's and V's. What are you going to do initially? Step one is identify the mesh currents, and that's pretty easy now. These meshes are staring us in the face. We now have this mesh, and it doesn't really matter if I call it I sub A, I sub 1. You just need to make sure you have unique subscripts. Let me call that I sub 1. And here, let's say is I sub 2. Just to keep the bookkeeping. So I've now identified I1 and I sub 2. And what I can, I hope, see or make a note of is the fact that I have a current source that really is only associated with one mesh. It's the rightmost mesh, that current source, which means that I2 is determined by that current source. It's given. If I know the current source I sub S, I know I sub 2. I've already defined that mesh current, but that mesh current I sub 2, if I ever see it in my formulas, I'm just going to replace it with that current source minus I sub S. Since the way I define my mesh current, it's opposite to how that current source is directed in the circuit. That means then that if I'm in step 2 and I'm writing my KVL equations for mesh circuit analysis, I only need to write one KVL equation. And that's the left, associated with the left mesh or mesh 1. I only need one KVL equation. And that's the KVL for mesh 1, which is minus V sub S plus R1 times I1, that's the only current flowing through R1, plus R sub 2 times, and we can write this initially in terms of our mesh currents. The current going down, the net current going down is I1 minus I2. This is now minus V sub S plus R1 I1 plus R sub 2 I1 minus I sub 2 is equal to 0. But in fact, in step 1, we noted that I sub 2 is a given if somebody gives us that current source value. That now eliminates one of the unknowns in this problem. Now we have one equation and one unknown. We can solve that for I sub 1. And we don't need to put it into a calculator. But if we were, what's the dimension of our resistor matrix? Let's do some of the combining. I have R1 plus R2 times I1. I then have a minus I sub S times R sub 2. That will be a plus R sub 2 I sub S. And let me put the V sub S on the other side by adding capital V sub S to both sides. Or now I'm going to ask my question again. What's the dimension of my resistor matrix? Here's where you might get confused. A matrix, well, yes, it's a 1 by 1 matrix. It's a scalar. It's r sub 1 plus r sub 2. This is our Ri is equal to V. This is Ohm's law again, but it's for a single equation. I1 is now V sub s minus r sub 2 I sub s. All of that would be given in addition to r sub 1 and r sub 2. If you said, well, I need a second mesh equation because I've now written, or I've labeled this with I1 and I2. What happens when we start to write KVL in the second mesh? Starting in the left corner, lower left corner, we would have R2 times I2 minus I1 plus R sub 3 times I sub 2. Then what happens? What's going to be the voltage dropped across that current source I sub s? It's going to be whatever it needs to be in order to deliver or produce I sub s amps going up from that current source. It's not going to be determined, but I could understand it much better if... Could we understand that voltage much better if we just labeled it? Now KVL is R sub 2 times I2 minus I1 plus R, so this is KVL mesh 2, R sub 2 times I sub 2 plus V sub I is equal to 0. But now we could find V sub I if we wanted it. If we've now found, we know that I sub 2 was minus I sub s, and we just found I sub 1 from that previous expression. We could now solve for, if we needed it, V sub I. But initially, we would just have to label it as an unknown voltage, an unknown variable, V sub I. It's going to be whatever it's going to be based on that current source delivering or supplying I sub s amps going up. What did we just find in this example? We had a current source that was only in one mesh. When a current source component, that's the current source that we were dealing with on the right-hand side, appears in only one mesh, we didn't have to worry about writing a mesh equation for that mesh. That mesh current, writing a KVL equation for that mesh current, it was already determined. I sub 2 was minus capital I sub s. Now, how could I change that up? Well, now, suppose we have this problem, and now the current source component is in more than one mesh. Do you see that? It's now shared between the left mesh and the right mesh. The current source is in between those meshes. So it's in more than one mesh. That's what I'm meaning by, is the current source component in one or more meshes in the circuit? And here, if we said, let's go ahead and label this as I1, and that is I sub 2. If we what do we know about V sub AB? The voltage dropped across that current source. Do we know it? Is it a given? I sub S is given. Do we now know what V sub AB is? No, we don't know it initially. So this is unknown. Initially, and we'll be able to find it if we can solve for the mesh currents I1 and I2. If we simply proceed as the standard process, we would say, okay, identify the mesh currents. I've identified I1 and I2. I have two meshes in that circuit. Now let me just start writing the KVL equations for each mesh in the standard way. The first mesh would be minus V1 plus voltage drop from left to right, R1, I1, and then we don't know the voltage dropped across that current source, so we just have to assign it an unknown label or an unknown value, V sub AB. The drop then across that current source from top to bottom is plus V sub AB. That's the end of that first KVL equation. It was minus V1 plus R1 I1 plus V sub AB is equal to 0. Yes?
So, because we're representing that voltage drop across I sub S as some unknown variable, we don't have to include I1 minus I2.
So now the question is, I was wanting to apply I1 minus I2 somewhere. Well, that's going to be next. We're going to have a constraint, just like we had a constraint equation when we were doing node voltage analysis and we had a voltage source between our nodes. Now we have a current source shared across two meshes. That's going to give us a constraint equation that we will be able to use, because right now we don't know what the voltage drop is across that current source. We don't know the resistance, so we can't multiply that resistance by I1 minus I2. So we can't do anything with I1, I2 yet. We just said let's label it as a voltage drop V sub AB. Now if we keep that same label, we can't change it now that we've assigned it. Now if we write KVL for the second mesh, it's minus V sub AB plus R sub 2 I2 plus V sub 2 equals 0. This is now minus V sub AB plus R2 I2 plus V sub 2 is equal to 0. And what do we have? We're given V1, that's a given voltage source. We're given V sub 2, that's a given voltage source. We know R1 and R2. We don't know the mesh currents, I1 and I2, and we actually don't know V sub AB. So we have two equations in three unknowns. But we can get rid of that V sub AB if we simply added these two expressions or equations. If I add these two expressions together, do you see that I would then be minus V1 plus R1 I1 plus R2 I2 plus V sub 2 equaling 0. Now I have one equation. I've eliminated V sub AB, which was unknown. And how could I have maybe written this down immediately without writing those first two mesh equations? Well, if we just look back at this circuit, I went minus V1 plus R1I1 plus R2I2 plus V2, and I'm back to the bottom. And what do you think I'm going to call that super duper thing? A supermesh. It's a combination of these two meshes. This is now a supermesh. And I could have immediately, when I see that that current source is common to two meshes, I could say, oh, I need to create a supermesh and just write one KVL equation around that supermesh, and then I'll have to write a constraint equation to give me the additional equation needed to solve for the unknowns. In this case, now that I just look at that supermesh path, do you see the KVL equation? Minus V1 plus R1I1. I use the same mesh currents plus R2I2 plus V sub 2. And this supermesh is now what results immediately right there. And I could have avoided those first two KVL equations. I essentially obtained them by just writing a supermesh. I have now one equation and two unknowns. I need a second or another equation. Since I have two unknowns, and I can actually write a relationship between that current source and my mesh currents, and that's the constraint equation. That's going to be obtained from the current source in the two meshes. How do I relate capital I sub s, little I sub 1, and little I sub 2? This we've been doing all along, haven't we? The last 2 days. That's a long time, huh? Capital I sub s is equal to, can you define that in terms of the mesh currents? What's the net current going up? That's capital I sub s. What's that equal to in terms of your mesh currents? 6I sub 2 minus 10I1? No, it's just I sub 2 minus I sub 1. I sub s, that's our constraint equation. I sub s is now equal to I sub 2 minus I sub 1. And that's our second equation. So here would be equation B, and here would be equation A. We can now solve those two equations simultaneously to obtain I sub 1 and I sub 2. And since everybody seemed to be excited about matrices, could we put that into a matrix formula? What's our unknown? We have two equations. What are the two unknowns in those equations? I2 and I1, I'm going to write them numerically. I'm going to say I1 and I2 stacked on top of each other. So my unknown vector is I1, I2. That's going to be multiplied by something to produce a right-hand side. If I plugged in B in the bottom row of that matrix representation, how would I write that? Do you see I need minus 1 times I1 plus 1 times I2, and that gives me I sub s. What if I now tried to put A into a matrix form? Now I might want to rewrite this as R1 I1 plus R2 I2 is equal to V1 minus V2. My right-hand side is V1 minus V2. R1 scales I1. R sub 2 scales R2. In a matrix form, there is my matrix expression. I could solve that for the unknown mesh currents, I1 and I2, if I'm given the information in the circuit. My voltage sources, my current source, and my resistors. Or you could solve that for I don't even know what I was going to say. You're solving it for, oh, you could solve it by 2 simultaneous equations. That's what I was going to say, if you don't like matrices. Let me give you a challenge. Suppose I give you the following circuit. And now the exam problem, the exam question maybe is solve this circuit using mesh current analysis. Besides your palms starting to sweat and your heart racing, what do you do next? That's normal, so don't freak out when that happens. That's a part of an exam, right? Is getting a little bit nervous, having the adrenaline kick in. That's what you want, so that you're on your game. How do we proceed? Can you see mesh currents? I can see mesh currents, right? And let's say that I just start going. Here's I sub A, I sub B, I sub C, and I sub D. Did you see 4? What else do you see if you've now quickly written down these 4 mesh currents? Do you see anything sort of collapsing or falling out? Suppose I call that I, hint, hint. We have a lot going on here, don't we? The comment from the audience just then was we have a super mesh. Does everybody see our super mesh? It's for mesh A and B. Super mesh is right here. And we could write a KVL for that. So we have a constraint equation. What's our constraint equation for that super mesh? Is that right? That's our constraint equation. What do we have in the top right-hand corner? Do we need to solve for I sub C? Nope, that's given now. So now really we only have 3 unknowns. 3 unknown mesh currents. What about I sub D? There's our traditional mesh. That we just write a standard mesh expression, KVL equation. Now we have a strategy. Our hearts calm down a little bit. We've taken a couple deep breaths. Now we just need to solve it. We good? And I didn't even have to pull a muscle. It's been a good day. I'll see you tomorrow.